Okay, take it away.
Yeah, so hi everyone. So my name is Zixin. So I'm going to be telling you about private key quantum cryptography with boson sampling devices. So I've kept the original title because I felt it was slightly more informative, maybe. Yeah, so the new title published is Photonic Quantum Data Locking. Yes, so when this idea was first conceived, I was just finishing my PhD, and now about approximately 4 years later, it is finally published. So here is a roadmap for where we're going. So I will first talk briefly about boson sampling, and then I'll discuss our protocol. And then I'll tell you about quantum data locking, and then I can show you a sketch of the security proof. It's a sketch because the real thing is about, I want to say 15 pages, but yeah, the paper is out there. So yeah, so I want to tell you briefly about how this paper finally came through. So in the first caption there, you can see that was submitted to the archive on, well, in May 2019, so that's just a little over 2 years ago. It was repeatedly rejected for PRL. And then the second screen cap there was one of John's attempt to get it published in PRL. So what he said was, oh yeah, so whenever you're writing these letters, you have to dig out their criteria of acceptance. And then at the time, he mentioned that one of the editors owed him a favor because he picked out the last one, which is exceptionally pleasing science aesthetically, one of the criteria. So he tried to play that card with that particular editor, which apparently owed him a favor. And that's also the card he used to get a paper through, which the editor wanted to go through. But alas, it didn't work. It was a nice try. Anyways, so yeah, boson sampling. What is it? So it is a non-universal model for quantum computing, which the task is this. So you have n single photon Fock states input into an M-mode interferometer, and the interferometer is chosen from Haar random unitaries. So if you sample the output photon distribution, it is proportional to the n by n submatrix of the unitary. So Shield show this. And then Aronson and Arkhipov show that if you have m much larger than n, so you have many more modes than compared to the number of photons, then doing the sampling is proportional to, well, they show that if m is sufficiently large, then the submatrix approximates that of a random matrix, and it is known that calculating the permanent is classically very hard. So to give you some intuition as to why this is proportional to the permanent, so if you have an creation operator AI acted upon by the unitary, then it transforms like this. So if you just look at two photons, then the probability of them ending up in two modes 2 and 3 is proportional to the probability of them, well, the probability amplitude of them both going straight through and of them swapping. And this operation is equal to the permanent of that particular submatrix. And if you don't know what a permanent is, it's simply the matrix determinant with all the minuses swapped for the pluses. Okay. And since the conception of the term boson sampling, every single major photonics group has been trying to do an experiment. It was very exciting at the time, because, well, it's still very exciting, because it was the first time that we have proof that a quantum computer may have some post-classical properties to, so even though this particular computational task is not particularly useful, it does show an exponential speed up. So, so I believe to date, Jiang Pan's group holds the record of doing an experiment with 20 modes, 20 photons in 60 modes. Okay, so, so this is the intuition behind how this project was formed. So we know that for boson sampling, you shoot in an array of photons, and you know that at the output, there's going to be a large photon number path entanglement. And we know this is hard to crack classically, but what about by a quantum computer? So here we have a first information-theoretic proof that boson sampling is useful for cryptography. And by useful, I mean that we can either do quantum key distribution or to encrypt a message that's much longer than the key. And the latter is what we will concern ourselves with. And then later, we also move out of the no collision regime. So that is the boson sampling regime, where you have many more modes compared to the number of photons. We show that this could provide a very efficient scaling of the Hilbert space. So we have something like a quantum Enigma machine. And for those of you who may not be familiar with the Enigma machine, I will tell you about this now. So Enigma machine was an encryption device that was widely used by Germany during the Second World War. It looks like this, and the image is from Wikipedia. So it works basically like a substitution cipher. So for example, if you have a plain text alphabet that goes like this, you might swap out the A for an L, a B for a U, and so on and so forth. But after each letter, the substitution rule would also change. So at the time, this was computationally very hard to crack. But obviously, we know that Alan Turing helped work on the machine, which indeed cracked that. And the mistakes that Nazi Germany made was that they were using the same key over and over again. So obviously, this was breakable by a brute force method. But on the other hand, when you have a quantum machine, one thing you have on your side is that you have the known cloning theorem. So when you measure it once, it's gone. Right, so that's what we're aiming for. Cool. So now I can tell you about the protocol. So here, Alice wants to transmit a message to Bob. So they both hold an M by M interferometer, and the code words are chosen from the M choose N possible configurations of photon input. So each round, Alice chooses a code words, and if Bob gets the perfect state, log M choose N bits are transmitted. And here, Alice and Bob pre-share an unconditionally secure K-bit secret key. Well, log K-bit secret key. Good. There. Okay. What happened here? So in advance, but not necessarily in secret, Alice and Bob agree upon a set of K random M by M unitary matrices. So if you share a particular key of K bits, this little k bits, then this will correspond to the particular unitary u little k. So now Alice encrypts the quantum state by applying the particular unitary associated with the secret key, and she sends this over to Bob. Now, upon receiving the state, Bob, because he knows the secret key, then he knows what Alice has implemented, and then he applies the inverse unitary. And because Alice has applied a unitary and Bob is applying the unitary inverse, then the interferometer turns into the identity, and Bob retrieves the code word by simply measuring photon counting. Okay, so that's the protocol. So is there any questions so far? Sometimes I'm in the habit of going too fast.
I have a question. You might have said it, just a clarification. There's K unitaries, there's big K unitaries, so the key should be log K, right?
Yes, yes, that's right. Sorry, yeah, that was the typo. Log
and
K
then
bits.
the other question is, these unitaries act, they're unitary operators and the mode operators, right? Like,
yes, that's right.
They're also unitaries in the Hilbert space, but the way that you're thinking about them is in terms of the mode operators, right?
That's right. So it operates on the mode, on the spatial modes, because it's very difficult to implement a hard unitary on the Hilbert space.
Yeah, and then they can be realized by linear optical circuit, right?
That's right.
Okay, thank you.
Yeah, so if we were to implement a hard random unitary on the actual Hilbert space of the, n photons and n modes, that will require a lot of very difficult gates to. Yeah, I should have mentioned that's one of the strengths of the protocol. Linear optics and photon counting. That's what we need.
I think just as a side note, I think hard random unitaries in the full Hilbert space, I don't even know if it's well defined because it's infinite dimensional. But that's a separate discussion. I don't know if there's a well-defined notion of that.
I mean, we can. I guess you can define this thing called a epsilon net. So or in the security proof, or for some others, you can sort of, depending on the dimension of the Hilbert space, you can choose, how and the security parameter, you can choose a net of these things to be so that they are close to your metric by some distance.
Okay.
Yeah, but
I have another question. Do you need to feed your birds?
Not yet.
Okay. All right. Just kidding. Please continue.
Okay, so I will show you the results first. So here we're defining the net communication rate as the number of bits transmitted, so that's log m. Subtract the number of bits consumed, so that's log k. So here we're choosing the number of photons to scale as, the number of modes to scale as the number of photons cubed. And log m here is plotted by the blue solid line there. And down below are log k for different security parameters. So as you see, the net communication rate here scales exponentially between as you grow the number of photons. So basically we have our first task accomplished. So that is, we can encrypt a much longer message using a very short key, using a shorter key. So now we can actually go into the framework and the security proof. So what is the relationship between our work and Boson sampling? So we've used technical results from the original Aronson and Arkoff paper. So in the Boson sampling regime, these are crucial to calculating the key consumption, but the classical computational complexity of Boson sampling is not required in the security proof. So we argue that this is a strength of the protocol because we don't need to rely on the complexity of the classical computational complexity. So we go beyond the no collision regime. What does this mean? So when you're performing boson sampling, the assumption is that because you have a much larger number of modes compared to the number of photons, the probability that 2 photons end up in the same mode is suppressed. So with very little probability, you end up with 2 or more photons. So we have to, but obviously that becomes very inefficient in terms of the number of modes that you're using. So we go beyond that later, and we end up injecting a similar number of, well, not similar, but a number of photons which is similar to the number of modes. So in the security proof, we do have to use the accessible information as the security quantifier, and this is so the enhancement is provided by the quantum data locking effect. But unfortunately, because we're using the accessible information as opposed to the high-level information, it means that we have to impose the bounded storage model for quantum memories, which means that we assume that Eve has a quantum memory which is going to elapse after a known given time. So it can be perfect up to a certain time that is known, and then after that it dies. And this is just so that we can say that after a particular measurement, then Eve's information is bounded by a certain amount, and I'll go into that right now. So I'm guessing everyone here is more or less familiar with the mutual information, that kind of formality, or would you like to? Oh, okay.
You should review it briefly. Yeah.
Okay. Yeah. So I will briefly review these information theoretic terms for those who are not familiar. So if X is a random variable with m potential outcomes, each occurring with probability P of X, then the entropy of X is given by the negative of the summation of P of X multiplied by log 2 of P of X. So this tells you how much information you get on the variable X by measuring it. So now if you have 2 variables which may be correlated, then we can define a mutual information quantity, A and B, and it's given by HA of X plus HB of X subtracted by their union. And so the mutual information of B describes the degree of correlation between these 2 random variables. So if A and B are 2 communicating parties, you want the mutual information to be big. And if one of them is an eavesdropper, then you want this quantity to be small. Right, okay. And the accessible information is defined as the maximization over the mutual information of these 2 variables. So did I confuse anybody? Okay. Speak now or forever hold your silence.
There was a question regarding the accessible information as to what the maximization is over.
So it's measured, okay, so it's maximized over all the possible measurements. So here, if you have an eavesdropper, then if Alice is sending bits over the channel, then it's maximized over all the possible measurements that Eve can do, which we'll actually go into very shortly. Yep, so now we can talk about the quantum data locking effect. So if Alice is sending a message to Bob, then if Alice chooses all the code words with equal probability, then the density matrix that Bob sees is this. So you have an average over all the different code words when Bob has access to the secret key. So we can write this as the mutual information between Alice and Bob, which is when Alice is holding the random variable X and Bob holds the measurement Y as well as the secret key K. Then their mutual information is equal to log m bits. Okay, slow down, go back. On the other hand, if Eve does not have access to the secret key of k bits long, then Eve sees the density matrix as an average over all the different encryption unitaries U summing from 1 to k. And now we want to bound the mutual information between Alice and Eve when there are log k bits missing. Okay? So, so classically, there is this inequality which states that the difference between these two mutual informations is upper bounded by log 2 of k. So in other words, this is a rephrasing of Shannon's theorem. Okay, why does it keep doing that? Where if you have a secret key that is of log k bits long, then you cannot hide more than k bits in your message. Right, but on the other hand, if you encrypt your information in quantum states, so if psi is quantum, then the difference between these quantities can be much, much larger than log k bits. And this is a violation of the classical inequality. And this is something that's uniquely quantum and has no classical counterpart. Okay, so is everyone happy with that?
I actually have a question. Can you explain? So there's equation 4 and equation 5. Mm-hmm. And, when we calculate the accessible information, we do get a classical mutual information, right?
Yep.
And so why does inequality 4 not apply to the expression on the left-hand side of 5? Okay,
so yeah, so the short answer, and maybe also the long answer, is that the so in 4, all the variables are classical, so all the states are classical, whereas in 5, you are embedding your classical variables into quantum states.
Okay.
And so that's the quantum data locking effect. So what's a better way of explaining it? So if you look at the quantum mutual information, the advantage disappears. Mm-hmm. And the difference between the quantum mutual information and the accessible information is the quantum data locking effect, if that makes sense.
I think I might have a different way of understanding it. And I actually worked on this topic like 10 years ago, so I'm trying to remember everything. But I think your equality in 4, it allows you to write a conditional mutual information, right? Is where the difference of accessible informations, I think, cannot be written as a classical conditional mutual information because they're different. They lead to different distributions, right? There's like one distribution for the accessible information on the left and another one for the accessible information on the right. And then I think you can't combine them as a conditional mutual information. Does that make sense?
I think so, but I can't compute the quantities in my head very effectively.
Okay, but I
Yeah.
think like anyway, I think that's one way of understanding it.
Yep. So the quantum data locking effect is what we're taking advantage of here in our protocol. Yeah, so now we're ready to talk about this security proof. So the goal here is to upper bound the accessible information between Alice and Eve with high probability. So what that means is that when you want to bound this quantity to within epsilon, where epsilon is a very small number, and you want the protocol to not fail with high probability. So, yep, so the accessible information there on the screen, as you've seen before, is valid for the assumption that Eve has finite quantum memory. So if we impose this assumption, then the protocol becomes composably secure again. So what that means, so that's a technical term, which means that if you have a component which is, so you have multiple components in your system, and one thing is epsilon 1 secure and the other thing is epsilon 2 secure, then your combined system is no more than epsilon 1 plus epsilon 2 insecure. Anyways, so the state that Bob sees is given by this expression over here in equation 8, which we've seen before. And the density matrix as seen by Eve is given by this expression over here, which we've seen before. So we have an auxiliary system X, which describes which code word Alice has chosen, which Eve does not see, and we have an average over the different encryption unitaries, which Eve has no access to. Right. So I'll just leave that quantity on the screen here. So the starting point is that quantum mechanics dictates that the best measurement that describes what Eve can do is described by a set of POVM elements given by this expression over here, where you have alpha of y multiplied by these 5 vectors. And when you sum over y, these elements, you get the identity operator. So when you apply 11 to Eve's density matrix, you end up with this expression over here, where there are 2 terms. So we're going to bound these 2 terms separately. Okay, so I'll just leave that on the screen for a minute longer, well, a few seconds longer. So you're overlapping row A of E by the element alpha y, rho phi, and ket phi on the 2 sides. And you end up with this expression over here.
I think there's a minor typo in equation 11. The phi should have a subscript y, right?
Yes, that's right. Sorry, that is a typo. Yeah. It's like I've given this talks more than 3 times, and you're the first person to pick up on it.
I think most people, they just fill it in,
Yeah. Okay. So we're going to bound the first term using the matrix-Chernow bound. So the matrix-Chernow bound states that if you have a collection of d-dimensional Hermitian matrix valued random variables with expectation value mu times identity, then when you add up a number of these terms, well, t of these terms, then the probability that it deviates from the mean by delta is exponentially suppressed by a factor of both t and delta squared. So here, the expectation value averaged over X would be given by the maximally mixed state. So I think for our purposes, we have to use a slightly modified version to account for photon counting, but it's too complicated and I won't show it here. Yeah, but the gist is that when you apply the matrix Shannon bound to the first term that we want to bound, then we end up showing that the probability that this quantity here deviates, its eigenvalues deviates from epsilon is exponentially suppressed, and this holds true with almost unit probability. Right, and now we want to bound the second term because now these are not matrices, and yeah, so the quantity we have to use is the Macquarie tail bound. And it is a very similar statement to the matrix Shannon bound, except this time it applies to real random numbers instead of matrices. So yeah, so if you add up a bunch of these quantities, or k of these to be more precise, then the probability that it deviates by tau from the mean is once again smaller than the exponential of negative k times tau squared. So a very important quantity to note here is the ratio of the expectation value squared to the, this is flipped over. So the expectation value of x squared divided by the expectation of value x squared. So this quantity here, which we call gamma, dictates the secret key consumption required by our protocol to ensure that the protocol is still secure. And if we do have photon bunching, that modifies this security parameter, and that's where also, I think it's on the next slide. Yeah, so the particular quantity gamma here is also where our protocol is tied in to Boson sampling. So the actual quantity that we want to calculate is the overlap of Eve's vector with the unitary operator acted upon by a typical code word. And this is proportional to the permanent squared. And we can calculate the mean value. This is n factorial divided by m on n. Yeah, so this is easy to calculate. And the other quantity that we need to calculate is the fourth moment, which is the permanent squared. And this number we extract from the Arison archival paper because it was non-trivial to calculate if you're not a computational scientist. And when you calculate gamma, this turns out to be bounded by 2 times n plus 1. So, so spoiler alert, if log gamma is the number, is the key consumption, then you're transmitting log m choose n bits, and one of the terms scales as log n bits. Right, so this is a huge difference, and it doesn't scale with m. Okay. Yeah, so everything that I've described so far applies to one value of x. So we've talked about photon bunching more or less, and then now we have to extend the protocol to all possible code words, and then we extend this to all the possible different vectors that E can use. So I think this is where an epsilon net comes in, but once again, I won't show that on the slides here because it's way too complicated. And when you put the above results together, we do end up bounding that the mutual information between Alice and Eve is smaller than 2 times epsilon times the number of bits transmitted, provided that log of k is larger than log of gamma plus log d on m. So d on m is, so d is the dimension of the entire Hilbert space of the n photons in m modes, and that's because d is larger than m, especially if we're not in the boson sampling regime. So in the boson sampling regime, this number approaches 1. And you have a term which is proportional to log of 1 over epsilon, where epsilon is a security parameter.
Sorry, can you just remind what little d is?
Oh, sorry. So d is the dimension of the entire Hilbert space.
And it's finite dimensional because you're sticking to these single photon states.
Yeah, so sorry, I have it somewhere later in the slide. So if you have
Okay.
n photons in m modes, d is given by n plus m minus 1, choose n.
Thank you.
So this is larger than our code word space, because our code word space is m choose n. Okay, I should have had that on that slide there. Okay, so we can talk about the probability of failure of the protocol. This is all very nice and complicated, but the only thing I want you to look at is that you have the secret key log k, and everything sits inside an exponential, and we can make this go to 0 very, very fast if we choose k to be larger than this quantity over here, which is a simple algebra. And when you take the log of k, this ends up being this expression over here, which is what we've seen before. And this dictates the number of secret bits required to keep the protocol secure. Okay. All right. So is there any questions so far? Okay, I'll keep going. So yeah, so everything that we've discussed so far described the one-shot scenario where you have like perhaps a big state and then you encrypt it and then you send it over. So so that's not very useful in a realistic quantum communication scenario, because what you would typically want to do is to repeat your transmission with a state of the same photon number over and over again. Right, so you want to send many of these signals, and Bob wants to measure many times. So you want to send, so if we define nu as the number of signals that you end up transmitting, then the total state is given by a tensor product of all of these. But because this takes a tensor product structure, then you end up with a very nice result here, where all the quantities that we talked about before is simply given by, so there's a particular parameter C-min, which I didn't mention before, but this parameter ends up getting a factor nu. So C, the parameter C ends up being C to the nu, and if you have a parameter gamma, it becomes gamma to the nu. So when you take a log of these, you end up adding these together. So which is to say that this protocol scales up pretty nicely, and everything applies, and everything works.
I have a question, sorry.
Yep.
The bold U, you might have said it, is that a tensor product of?
Yeah.
Okay, all right.
Yep, sorry, yeah, I've been sloppy, but this ends up being whatever UKs you've chosen nu times.
Yeah, all right, and so it's a lot easier to implement that way. Right?
Yes, so it's much easier. So, here before so this is all very well nice to talk about having n to 40 photons, right? But if you tell experimenters I want 40 indistinguishable single photons in a 40 cubed interferometer, they're definitely going to laugh at you. So in the limit that you have a very large number of signals that you send through, the number of bits that you require per transmission ends up being log gamma plus log, the dimension divided by the number of bits that you transmitted again. So let's look at how tolerant to loss this is, because it's not very good to have a protocol that works only in the limit where you have unit transmission. So for this particular example, we've chosen to have 4 photons in 20 modes. And in purple there, we have the transmission parameter 90%, and you have in green 70%, and 90%, 70%. Sorry. So this is unit transmission in purple, and then you have 90%, 70%, and at 50% transmission, you have the key rate, which is just above positive. And then the referee was like, oh yeah, so this is all well and good, but how does it compare with BB84? Well, I'm quite glad that they asked, because that gave us our money shot there, which they also hated. But anyways, so the question was, how does your protocol perform in terms of the information density per mode? So let's talk about BB84 first. So BB84 can, in the perfect scenario where you're using a bias basis, so which means that you're predominantly using the same basis, so you don't lose the factor of half. So in that particular scenario, you will transmit at most 0.5 bits per mode, right? Because you have, so each round of the BB84 protocol, you transmit 1 bit, but you're using 2 modes, so it's you get at most half a bit per mode. But for our protocol, because we are transmitting log m choose n bits per round, and when you divide this by m, and this number is potentially larger than a half, right? So our protocol is in principle, or at least what we found for the parameter space that we search here, it could beat the information density of BB84. And that's because in BB84, your single photon is restricted to travel between these 2 modes, whereas in our interferometer, it's allowed to delocalize over the entire m modes. Right, but of course, you could argue that this is comparing apples and oranges, not quite comparing apples to oranges, because we need the bounded storage model, and that's why they tend not to like it. But oh yeah, I should talk about the graph. So here we have BB84 in direct reconciliation plotted in red there. So it only makes sense to compare our protocol to BB84 in direct reconciliation, because our protocol is a direct reconciliation protocol. So what that means is that you're encrypting all your information at the point of transmission. So I guess now the workhorse of quantum communication or quantum key distribution is reverse reconciliation. So I don't know too much about that, so I won't talk about it. So yeah, but I've left that as a comparison in orange there. So you see that if we're using 40 modes optimized over the number of photons that you transmit at the beginning, depending on the loss parameter, then our protocol can potentially beat the BB84 indirect for all loss parameters. Yeah, so I guess you can improve this even more if you go to higher higher mode numbers. And we expect that if we do end up deriving a security proof of our protocol in reverse reconciliation, we can expect similar behavior. So our protocol could, in principle, beat this orange curve. Okay, So in conclusion, we have a quantum private key encryption protocol, which we claim to be the first actual application of boson sampling, as in the original single photon Fock state into an M-mode interferometer setup. But we went beyond that and showed that we have an information-theoretic proof that holds for any number of modes M and the number of photons N. So in the future, there are a couple of things which we might want to look at. So yeah, we might want to remove the bounded storage model assumption. So scattershot or weak coherent states might also work, and how we might do quantum error correction, or sorry, classical error correction, privacy application, so on and so forth. So yeah, so the last point there, it is natural to consider spatial modes for our interferometer, but that's not necessarily the most efficient way or the most phase stabilized way of implementing it. So you could also choose to say use a optical angular momentum type implementation, provided you can interfere them. Okay, so yeah, giving acknowledge where it's due, the protocol was first conceived by, I guess, John and Peter and Dominic somewhere at on the Formula Lounge at Macquarie University, I want to say 4 or 5 years back, but we have no idea how to do the security proof until I dragged Cosmo into the project. And I want to finish up with a quote from John there. So, after a couple of glasses of wine, John was or even without the glasses of wine, John was telling the story of Yang and Lee. So when they were doing the symmetry experiment, sorry, go back one step. So the story of Yang and Lee, and when they were doing experiments together, they would alternate between who's the co-author when they're writing a paper. But when they finished the symmetry breaking experiment, one of them went to the other and said, I know it is your turn to be the first author, but I want it to be me this time, because they both knew that the result would lead to a Nobel Prize. And story from John was that apparently after that, they never spoke to one another again, apart from shaking hands at the Nobel Prize ceremony. And then after that, he yelled, no, sorry, I'm not supposed to swear, right? So I'll leave that quote there for you to read out. So yeah, so he doesn't care if you have a Nobel Prize. So yeah, so I would like to thank him for the encouragement and support for the years I've known him, which has meant a lot to me when I was at a very vulnerable time in my career. So yeah, I would like to thank you for your attention.
All right, thanks a lot for that. Thank you for the special dedication at the end. I have a number of questions, but I've been asking a lot of stuff. Mm-hmm. Does anyone else have, yeah, so Vishal, do you want to come up here and ask your question? Because I think, I don't know if she'll be able to hear you.
I'll just say it here. My question is, what do you mean by using weak coherent states, which you mentioned as possible future work?
So that just means that we want to replace our single photons with weak coherent states. So
small alpha.
Okay.
Yep.
Yeah, they approximate a single photon, like a common experimental approximation.
So yeah, so that was because weak single photons, or weak coherent states are much easier to produce than single photon, than perfect single photon Fock states.
All right. Any other questions? Any questions from the Zoomers online? All right.
Can you hear me?
Oh, go ahead.
Can you hear me? Yeah.
Yeah.
I don't see my face, so I'm sure.
We can hear.
I can hear you. Yeah.
Anyway, Zixin, yeah, nice to see you.
Nice to
One
meet you.
question is the Eve has memory time of finite, you said.
Yes.
Yeah.
Yes.
But that time is not in the anywhere in the formula. So
right.
I assume that this is zero.
So this is general. So I forgot to mention that what that means is that we require that Eve has a finite quantum memory time, but we know what that is. So, so after the transmission, they just wait until they're sure that Eve's quantum memory has died, and then they can proceed with the post-processing. So I guess why we need that there is that so we have a secret key that's locking a much longer message, right? So, that's the strength of the protocol as well as the Achilles heel. So because you're using so little information to lock such a long message, any information that's been leaked to Eve, is going to help her unlock a large part or potentially unlock a large part of your message.
Okay, yeah, thank you. Yeah.
Cheers.
For another one, this is impressive that your scheme with m equal to 40, it's better than the BB84 in all the transmission regime.
Well, but yeah, so that's because we're comparing it to BB84 direct reconciliation, where the information goes to 0 at transmission parameter eta. And transmission parameter 0.5. So obviously currently in realistic quantum key diffusion experiments, the transmission parameters can be much smaller than that. So yeah, so I don't think we can claim that this is actually useful unless we can push this blue curve to be above the orange one. But that's it's work in progress and also open to whoever wants to claim it.
Okay.
Because we don't know how to do it yet.
On the other hand, m equal to 40, what would be the difference between m equal to 20 and m equal to 40? It's more number of modes, like twice.
A number of modes. So yeah, basically you increase. So here it's not just the modes, right, that we're considering. So it's also we've also optimized the number of input photons into the modes. So that's a thing that I haven't shown here. So for perfect transmission, the optimal number of photons at the input. So right at this point, can you actually see my mouse?
Yes.
Okay. So yeah. So at this point, at the perfect transmission, the number of photons is approximately 1/3 of the number of modes. So here n is approximately 13, and then it actually decreases depending on the loss parameter. So yeah, we got very excited when we saw this, but once again, the referees hated it. Well, the PRL referees hated it.
Yeah. One last question is the K, the key part, the use of K, the unitary operation for the key, that m equal to 20 and m equal to 40, that the UK would be all different.
Yes, that's right. Yeah, so that will depend. So I've hidden it here. So K would scale approximately as log gamma, and so in m equals to 40, that kind of configuration, you have the photons are heavily bunched. So you have to compute what gamma is, and this parameter, so d on m, once again, is much larger than 1, so you have to consider that. But all of these parameters you can numerically compute. And after optimizing, you can figure out without too much difficulty.
Yeah, of course, the implementation of UK is considered to be perfect.
Yes, that's right.
Mm.
So we argue that by saying the errors in optics is mostly losses.
Right. Okay. Yeah.
So we consider losses.
Yeah, fair enough. Okay, that's it for me.
All right. Any other questions from people on Zoom? Okay. I actually have 3 questions if you have the patience for me.
Definitely.
The first is, at the beginning, you talked about, you made this comment that the proof, it's information theoretically secure, which is great. My question is, if you were to only guarantee some kind of computational security, would you be able to achieve even higher rates?
I believe somebody else has looked at that problem, so they explicitly considered using the complexity in the proof. I haven't read that paper properly, but I can point you to it.
Who is that?
God, I don't remember the name, but I think the paper came out at more or less the same time as when we first. But
Wow.
apparently their paper got rejected from PRA, so the editors liked it even less.
Interesting.
I can find out, yeah.
Well, that sounds interesting. So I don't know why the editors would be about it.
Okay, so the problem with using the actual complexity, the computational complexity, is that you would also need a large number of photons for it to be valid.
Uh-huh.
So, you don't end up with problems calculating the permanent until you're at, above n equals to 20, right? So.
Oh, okay. That should be a very large number of
Yeah.
nodes. Okay. I don't know. I mean, I guess you could have the same criticism for boson sampling itself. So,
well, John kept arguing that it's supra exponential because not only the permanent sampling thing is valid for one particular configuration, right? So, and then you can also claim that because you have this Hilbert space that's being blown up by a factor of this factor. So where is it? Yeah, so the dimension of a Hilbert space is being blown up to this factor. So that makes it even harder because you have to calculate exponentially many things.
mm-hmm. Okay.
So you have exponentially number of permanents to calculate.
Right.
And each of those things is exponential.
Okay. My next question is more of a comment. If you could go to the slide with the comparison with BB84.
Mm-hmm.
I actually think it is a comparison of apples to oranges because, this photonic data locking, it's a protocol for transmission of a private message and not for generation of a key, right?
Yes.
And,
so,
and so like is where the reverse BB84 is more like a protocol for key generation, which eventually you combine with a one-time pad. And so I just kind of think they're a little bit on different footing. I guess this point is debatable, but like I wouldn't even have included the BB84 reverse on this plot because I think it's just a different task. It's a different style of protocol.
Yes, you're right. But sorry, the referee asked for that particular plot, which we didn't include in our final paper. But I guess you could argue that quantum key distribution is also a key growing protocol. You need a seed to begin with, right, with the initial authentication stage. Right. So, if we consider our protocol as a key growing protocol, then you can kind of compare them.
Okay. Anyway, so that was more like a comment than a question.
Mm-hmm.
And the final question is there experimental interest in implementing your protocol? I mean, like, I know that Cosmo worked with experimentalists at MIT, like around 2015 to implement some kind of data locking, but this is a very different way to implement it, and maybe it's realistic.
Yeah, so like I want to say maybe 2 years ago, we've heard some noise from Jiawei Pan's group to say that
Oh.
they might be interested, but we've never had an update from them. But I guess the thing is like, you know, for this protocol to be, so one of the biggest criticism is that if we want to use this as a practical quantum communications protocol, then the very fact that we're implementing the bounded storage model makes it vulnerable to attack when quantum memories come online.
Yeah.
So
but
they
they're
were
not,
like,
and it's a long time away, you know.
yeah, but I have strong opinions on that. But
Okay.
yeah, as in, you know, I strongly agree with you. But they seem to think that why are we investing in this infrastructure when we know that at some point in time it's going to become vulnerable to attacks, where, you know, when we can invest in quantum key distribution, which is known to be secure by the laws of physics and blah, 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 blah.
It's interesting to learn that about Pan and his group. Yeah.
Yeah, but yeah, we haven't heard from them, presumably because whatever reason.
All right. All right. I don't know if there's any more questions, so I think I'll stop
I have
recording.
one
Oh,
comment.
All right. Yes.
Did you share that?
Go ahead.
Okay. Yeah, this is for the last slide, the Li and Yang thing. And yeah, Li and Yang, they were serious. It was not the experiment.
Oh,
Yeah. They are serious.
you know,
So
that was a second-hand story from John. You know,
Yeah,
perhaps his philosophy is never let facts get in the way of a good story. But but I very enjoy that.
yeah, of course.
That story from him. Yeah.
All right. Well, with that, I'll hit stop recording, and